By going through the validation exercises, we learned how to create one element, i.e. a beam with one element, set up boundary conditions, define material properties, subject the beam to an incremental temperature increase, and finally, incrementally load the element. This assignment is just an expanded version. So the upcoming assignment, as you can see on this slide, is an expanded version of the validation script that we have already created. Consider a 9-meter IPE 330 beam, so the same cross-section, this time with 10 equal elements. It is loaded with 10 kilonewton per meter uniformly distributed load, and then subjected to a 30-minute ASTM E119 ISO 834, or in other words, a standard fire curve. It is subjected on all sides except the top flange, as you can see over here. So because there's a concrete slab usually on top of these beams, this part, the top part of the top flange of the beam, is not subjected to a fire curve. Assume a simplified temperature distribution across IPE 330 section as shown. So we are assuming that the bottom part is going to have a high temperature at the end of the 30-minute analysis, and this will be ramped up from 20 degrees of Celsius all the way to 825 degrees of Celsius, and the top part will ramp up to 690 degrees of Celsius. So there will be a temperature gradient cross to cross section at any given time. The midspan deflection, as well as axial load and moment history, will be monitored for this beam in this exercise. In scenario A, we will conduct a parametric study on the beam with pin roller, pin-pinned, and fixed boundary conditions. So we're going to look at boundary restraints and the effect of those on the beam behavior. The internal forces and vertical midspan deflections will be compared. In scenario B, we're going to look at another set of parametric study, this time on the utilization ratio. That means how much the beam is initially loaded compared to its bending capacity. So we will keep the 10 kilonewton per meter at first, and then we're going to have a much lower utilization ratio, such as 0.1 kilonewton per meter uniformly distributed load. So we're going to see the effect of initial loading conditions on the thermomechanical behavior of the beam. Again, the internal forces and vertical midspan deflection will be compared. Before jumping into comparing internal force time history graphs, I'd like to simulate the formation plot of the beam, as well as axial force, shear, and moment diagrams dynamically. This is a recap. The beam is pin-pinned in this case. It is loaded with constant 10 kilonewton per meter uniform distributed load, then subjected to a standard fire curve for 30 minutes. This graphical interface reads the output of OpenSees Pi and visualizes the diagrams along the beam length at each time step. You can create such graphical yourself by yourself, or some available commercial software that's written specifically for writing and reading the OpenSees Pi outputs. As you will see, the axial force and moment diagram will continue to change along the beam, but shear, which is directly related to the gravity load on top of the beam, stays almost constant with increasing temperature. All right, so what we're doing is we have created the beam. So we started the analysis. The beam will deflect. As you can see, the midspan deflection is over here. And this is the end of the analysis at 61 steps. Now we're going to look into F1, which is the axial internal force inside the beam, along the beam. And we're going to scale the diagram accordingly. So you can see it will start at compression, very large compression, and then towards the end of the analysis, it will actually switch to tension, which is colored in red. So the beam will actually hang on its supports in tension, like a cable. And next, we will go to F2, which is defined as shear. You can see a uniform distributed load will have a shear diagram like this. And you can see that along the entire analysis, the shear diagram does not really change. That just tells us that the gravity load stays constant. And lastly, the bending moment diagram for a uniform loaded beam will look like this. And it will increase initially, and then towards the end of the analysis, it will converge to 0 throughout the entire beam. And again, the beam will start acting as a cable, because cables do not have any bending moment. Okay? They don't carry or resist to any bending. So at high temperatures, as you can see, excessive vertical deformations cause the beam to develop tension while it is still heated and hang from its connection. At these moments, the moment along the beam is close to 0. The beam starts to act as a cable. So just to recap, we will have a continuously changing axial load and moment diagram. In a very simple structure like this, we will still have that in a thermomechanical analysis. And we will also have an almost constant shear diagram as long as the gravity loads are not changed throughout the analysis. And towards the end of the heating phase, we can have hanging structure, so a beam behaving like a cable at high temperatures. Restraint conditions are vital for the structural fire analysis. It dictates this critical temperature of a member, which is the temperature at which the structure fails by any of the limit states. For example, it could be deflection limit, like a serviceability limit. It could be buckling capacity, tensile yielding, or rupture. This plot shows midspan beam deflection here versus time. The red curve is the midspan deflection when the beam is not restrained. So this red curve shows when the beam is a pin roller beam, as in the first case here. The midspan deflection gets larger as the beam is heated, since the stiffness of material reduces, in this case steel. Also, P delta second order effects come into play at large deflections, further increasing the deflection rate. The deflection rate rapidly increases to a runaway behavior, as you can see over here, until the beam temperature is high enough that the beam cannot withstand the gravity load, which is 10 kilonewton per meter applied to it. The critical temperature from the analysis at about 18 minutes closely aligns with Eurocode 3 Part 1, Part 2 critical time assessment or critical temperature assessment of 692 degrees of Celsius, as seen in the dotted black line. So the Eurocode proposition for critical temperature assessment closely aligns with what we get from the analysis of a pin roller beam. When the beam is pin-pinned, so it's translationally restrained at each support, the deflections are larger, and this is seen as the blue line over here. The deflections get much larger compared to the red line due to thermal expansion contribution to the midspan deflection. However, the beam does not fail in runaway and sustains the load even at 780 degrees of Celsius towards the end of the analysis at 30 minutes. When the beam is also rotational restrained, so we're talking about a fixed beam, which is seen as a black line over here, the deflections are not as exaggerated because we are basically having a rotational restraint at each end, which limits the deflection at the midspan. And but they do converge to pin-pin case towards the end of the analysis without a failure. So the deflections get higher and higher, and they do converge towards the end of the analysis to pin-pin case, and we do not also experience any failure up until 30 minutes. When the beam is unrestrained, and now we're looking at the axial force time history analysis over here. The beam does not develop any axial load as seen in the red curve. So the red curve, basically the beam fails at around 18 minutes. We do not experience any axial load towards for the entire analysis range. But when restrained, the general trend in the axial load diagram is that the beam goes under compression very rapidly due to conversion of thermal or free strain to mechanical strain. This increase will reach a maximum axial load capacity, Pmax, which is shown over here or over here. This Pmax could be dictated by yield or buckling capacity of the beam. Pmax is reached before the stiffness or yield stress of steel starts to reduce. So that means that the beam is at around 100 degrees of Celsius. So nothing material-wise did actually change until this Pmax is reached. At further heating, the beam compression starts to reduce, as you can see, because of two things. First, the mid-span deflection the rate of the mid-span deflection gets larger than the rate of thermal expansion. Second, the stiffness or strength of steel material starts to reduce. Because of those two things, we get a reduction, significant rapid reduction of the compression in both pin-pinned and fixed cases. Towards the end of the 30-minute heating period, the axial load in the beam drops further, starts to reverse from compression to tension phase. And this is very much visible for the pin-pin scenario, where we now get into tension phase rather than compression phase. This means that the beam starts to hang from its connections at the support. This is a very important concept, that the beam is still in the heating phase and not in the cooling phase of the fire. So we are still in the heating phase, but we are getting tension, which is very counterintuitive to a typical traditional engineer. Let's look into moment diagram and how that changes at the midspan in the end for the entire analysis. When the beam is unrestrained, the beam has a constant moment, which is seen as the red line here, at midspan during heating until runaway starts. This constant moment comes from the gravity loads, which are pretty much not changing. This is expected since the gravity load stays constant as seen in the red curve. When restrained, the general trend in the moment diagram is that the beam midspan develops moment due to gravity load. So that's in the beginning. But this moment increases due to elastic plastic centroid shift towards a cooler region due to P delta effect. We're not going to get into mechanics of this problem, but we're going to say that the counterclockwise moment at the midspan will actually increase. So there will be additional moment due to P delta effects and due to this shift in the centroid of the plastic and elastic centroid in the cross section towards the cooling region, which creates additional moments. And this can be actually seen in both pin-pin case as well as fixed case. This increase will reach a maximum moment Pmax, and this Pmax could be dictated by yield or plastic moment capacity of the beam. Mmax is reached before the yield stress of the steel starts to reduce at 400 degrees of Celsius. So this Mmax, the maximum moment or maximum moment over here, is going to happen when the stiffness already has been reduced, but not when the strength starts to reduce. So at around when the strength of the beam starts to reduce, we're going to get this Mmax. At further heating, the midspan moment starts to reduce because of these two things that we previously mentioned. The midspan deflection rate gets larger than the rate of thermal expansion, and the stiffness strength of steel material will reduce.